Good morning class and welcome to another lecture in sustainable energy technology. We will continue our discussion on battery based energy storage systems. In the previous class, we were looking at the physics of the battery systems when it is being discharged and charged respectively. So this figure, as we discussed in the previous class, shows what is happening inside an electrochemical cell when it is being discharged. And what we saw is in one anode, namely the negative side, in one side of the electrode, mainly the negative electrode associated with the negative terminal, you are getting a dissociation reaction which is consuming energy and creating electrons and ions. These electrons are flowing through the external circuit and are recombining in the positive electrode, which is the cathode for a discharge process, and this recombination is releasing energy. Okay. What is happening during the recharge cycle is that you are using external electricity or work to drive the electrons in the opposite direction. So electrons are going from the positive terminal to the negative terminal against the potential gradient. And at this point, in the positive electrode, you are getting a dissociation, the reverse reaction, that is the dissociation reaction. And in the negative electrode, you are again getting the reverse reaction for the discharge process, which is the recombination reaction. So in a battery, energy is being given to the external circuit during the discharge process, and energy is being absorbed from the external circuit during the recharging process. So what this means is, the net energy difference between the energy released during the recombination reaction minus energy consumed during the dissociation reaction is positive during the discharge process, whereas the reverse set is negative. So the overall two reactions are consuming energy during the recharge process and releasing energy during the discharge process. And this gives us an idea of how to evaluate the battery's performance. So if EA is the energy released per electron per unit time when ions and electrons combine during the discharge process, so energy released, so let's write that also. Per electron per unit time. Okay. Here also EC is the energy consumed per electron per unit time. When ions and electrons are separated during the discharge process. So the energy consumed during the dissociation reaction and energy released during the recombination reaction per electron transport per unit time. That is EA and EC. Then the electromotive force is the difference between these two. Okay, so the electromotive force is the difference between EA and EC, EA minus EC. Okay. Now the units of EA and EC is energy release, so it's joules per electron per unit time, so joules per ampere. So this is also joules per ampere and this is also joules per ampere. So the unit of this EMF, electromotive force, is volts. Okay. So what this energy difference per electron per unit time gives is the potential difference between the two electrodes. Okay. The potential difference under ideal conditions is EA minus EC, and this is called the electromotive force. It's called the force because it is what helps drive the current flow during the discharge process. Okay. The external force that needs to be applied to the system during the recharge process is the reverse of this. So minus epsilon, EC minus EA, because it's a reverse reactions are happening. So energy is getting released by the reverse reaction. So minus EC becomes plus EC and plus EA becomes minus EA. Okay, so the reactions are reversed, so the energy direction, release becomes consumption, consumption becomes release. Okay. So this EMF or the electromotive force is what a voltmeter will measure. between the battery terminals under open circuit conditions. So when a current, assume you have a battery and there is no external circuit. You put the two leads of the voltmeter on the two edges of the electrode and you will get a potential difference. And this potential difference is the open circuit potential difference when the resistance is infinity, and that is a reasonable measure of the electromotive force. However, when the battery is being discharged, right, so let's look at the battery situation again. This is the discharge process and current is flowing, right. Now there is a flow of charged ions from one electrode to the other within the battery through the electrolyte, and that will encounter some resistance. Okay, so the flow of charged ions will create its own decrease in potential because of the resistance encountered within the electrolytic solution. So the voltage across the two electrodes will be, as measured in the external circuit, will be the EMF epsilon minus the current flowing into the internal resistance of the battery. So epsilon minus I into small r, where small r is the internal resistance of the battery, which is a combination of resistance to the flow of charged ions in the electrolyte, other dissipation based losses, etc. Okay. So this is the voltage that is actually measured in the external circuit. When the battery is being charged, the external voltage becomes epsilon plus IR, because the flow has reversed. That extra potential is the extra potential to which the charge has to be driven, right, to get the reactions going. Okay, so it will be positive plus IR here. Okay. Now if you draw a battery circuit diagram, this is how it looks like. The battery is given by this symbol, this epsilon, the potential difference, positive terminal, negative terminal, the two electrodes, the internal resistance R, together is the battery. This is the negative end of the battery, this is the positive end of the battery. During the discharge cycle, current is flowing from the positive terminal to the negative terminal through an external load of resistance capital R, and the current is flowing is I, and the external voltage measured is the flow across this resistance by this current. So this is the voltage V. Okay, V is equals to I into capital R, correct? So in this case, the current that is flowing is the electromotive force, the potential between the two terminals, divided by the total resistance, which is the internal resistance small r plus the external resistance capital R, correct? So that is the total current that the battery will supply given the external load capital R and the internal load small r. So clearly, if the battery has a higher electromotive force or EMF, then it will be able to provide a higher current. Also, if the battery has a lower internal resistance, then also it will be able to produce a higher current given an external load. Okay. Now, one point I want to show you, this electromotive force is the energy difference between these two reactions, right? And when we looked at in previous class, the value of these voltages here, these are the electromotive force values for the various cells. Okay, and based on the dissociation and the association reactions happening, the energy released is based on the the two electrode materials. So depending on the material, you can get higher amounts of energy released than energy consumed, and you are getting a larger electromotive force. Or you can have lower to the lower end, that is the difference between the release and the consumption is lower, and you will get lower electromotive forces for these material types. Okay. And why is this important to the performance? As we can see, the external voltage that is available is also dependent on the electromotive force, as well as the external current that is available for a given external load. Now, we can also define the short circuit current when the external resistance tends to 0. Okay, when the system is short circuited, is given by capital R tending to 0, so epsilon by small r. So that's the short circuit current. So if you look at an example, Suppose you have a voltmeter that measures 12 volts across a battery terminal under open circuit conditions. Okay. So, open circuit conditions, your electrochemical cell, the potential is 12 volts. So, that is your electromotive force, 12 volts. However, when a load is connected that is drawing 10 amps of current, so the current I is 10 amps, then the voltmeter reading decreases to 11.8 volts. And we want to find the short circuit current for this system. Now, the electromotive force epsilon is 12 volts. When a current is flowing, the voltage measured will be electromotive force minus the current into internal resistance. And this value is 11.8 volts and the value of current is 10 amperes and the epsilon is 12 volts. So, putting these values here, you can get the internal resistance which is 0.02 ohms. Now, you can put the short circuit current using this formula here as the electromotive force by internal resistance, which gives you 240 amperes. The next important point is how much power is being supplied by a battery. Okay. Now, power is voltage into current, and what is voltage? Electromotive force minus current into small r, right? So, the rate of change of voltage with change in current given a constant electromotive force is minus r, right? So, dV di is minus r. So, the slope of the voltage to current curve is a negative straight line, okay, assuming that the internal resistance is constant, okay. This may not be the case. So, it is important to remember that if you increase the current flow too much, then there will be dissipation losses also within the electrochemical cell, which may increase the internal resistance smaller. However, for over a small range, ideally at least, the voltage to current characteristic curve will be a linear slope, negatively decreasing line. Okay. So, we can normalize this idea. The voltage is electromotive force minus current into internal resistance. So, voltage by EMF is 1 minus I by EMF into R, right. Now, I by EMF is the short circuit current, ISC, okay. So, voltage by EMF is 1 minus I by short circuit current, okay. So, basically measured voltage by open circuit voltage is 1 minus measured current by short circuit current, okay. So, if you plot these two units, V by epsilon and I by ISC, you will get a curve like this going from 1 to 1 at when I is equals to ISC, the external voltage is 0, so you will get 1, and when I by ISC equal to 0, we are open circuit condition, so again it is 1, okay, the voltage becomes the open circuit voltage. So, it becomes a linear straight line, okay. Now, we can also show that if we plot the power by the maximum power in the same plot, then it becomes a parabola, okay. So, the power curve is parabola, because remember power is voltage into current, okay. So, you can basically multiply these two values together and plot the value of power at a certain point, okay. So, suppose here you get the actual current and the actual voltage, multiply these two to get the actual power, okay. So, that way you can plot the power curve and you get the P by P max as this parabolic curve here, okay. So, this means that the maximum power point is somewhere in the middle of this current voltage characteristic curve, when there is sufficient potential gradient and sufficient current as well, okay, to get the maximum power output from the battery. This is, if you remember the voltage current characteristics of a solar cell, it is quite different from that. For a solar cell, it was a constant current source. So, with voltage, the current was staying constant. Here you have a linearly decreasing line for your current voltage characteristic. We can also do some further manipulations. So current is EMF by small r by plus capital R. So let us put a different variable Z as small r plus capital R, which is the total resistance, correct? Z is the total resistance. So the current is EMF by total resistance. So the rate of change of current with total resistance is minus epsilon by Z square. Okay, Z to the power minus 1, so it becomes minus epsilon by Z square when you differentiate, or minus epsilon by R plus capital R whole square. Then the rate of change of current with external load, di d capital R, is di dz by dz dr. Now what is dz dr? It's 1, correct? So this becomes minus epsilon by R plus small r whole square, di dr. So di d capital R is also this expression here, minus epsilon by small r plus capital R whole square. Remember, this is only approximately valid because it assumes that the internal resistance R is not affected by the change in resistance or the change in current, which is not strictly true. But this gives you the slope of the current with respect to changing external load resistance. And you are seeing here a quadratic curve. Okay. So current is decreasing quadratically with respect to external load resistance. And the voltage value is epsilon minus I into, there is a mistake here, just I want to correct that, I into small r here. Okay. And what is I? I is electromotive force by capital R plus small r into small r, right? So now you take electromotive force out, so 1 minus small r by capital R plus small r, so capital R by capital R plus small r. So the expression for the external voltage is the open circuit voltage into this ratio, the external load resistance by the total resistance. Alright, so this is another expression by which you can express the voltage. So then, using this expression for voltage and this expression for current, you can get the power, which is voltage into current, which is epsilon into capital R by capital R plus small r into epsilon by capital R plus small r. This is the voltage value, this is the current value. So the power is proportional to the EMF square into capital R by total resistance whole square. This is the expression for power at any given point. Okay. So given the external load, you can evaluate the power that is being delivered to that load. Okay. If the internal resistance is small, then this becomes R by R square, so it just becomes E square by R, epsilon square by R. This is the case for an ideal battery system. Okay. However, in general, obviously you cannot ignore the internal resistance, so you can never reach this max power condition. Now we can also find out what is the round trip efficiency of a battery. Remember, the round trip efficiency is the energy extracted versus the energy stored. So we can look at the charging process and the discharging process and get the net work output by work input during the charging process. And you get here the efficiency eta is 1 by 1 plus small r by capital R. Okay, so this is the extra value. Okay, and this is expected because you are driving that extra potential gradient within the battery, which is basically causing the extra value here coming. Okay, so this is the efficiency, round trip efficiency of a battery. So again, if the internal resistance tends to 0, then the round trip efficiency increases. Okay, now 2 points of importance. This kind of shows that if you want to have a battery with higher efficiency, you need to minimize the internal resistance of the battery as far as possible. So that's number 1. The second point to note is, at high powers, the internal resistance is likely to increase because at high powers, the rate of electrochemical reactions is increasing, so the current being generated is increasing. So there are greater non-idealities associated with faster chemical reactions compared to slower chemical reactions. So dissipations, heat losses, all of those increase. So internal resistance R increases as the current requirement rises. Okay. So what this means is your efficiency, the round trip efficiency is going to decrease. Okay. And this is a typical case that is common for all types of batteries. So this is the mass specific energy. How much effective energy your battery can store and deliver. How much effective energy your battery can deliver to the external circuit. That is the specific energy. And this is the mass specific power. How much power it is delivering per kg of the battery material. And this is how much energy it is delivering per kg of battery. So this is the rate of energy transfer and this is the total energy transferred. Okay. And you can see that at low powers, the mass specific energy of all batteries are higher compared to the same situation at high power values. So for example, if you look at a lithium polymer battery, when the power requirement is say 3 or 5, 2 watt per kg, you are getting a energy storage density of around 180 watt hour per kg. Whereas when the power requirement increases to 100 watts per kg, the same battery's energy storage ability decreases to around 140, 145 watt hour per kg. Okay, so you see the large drop. Similarly, if you see a sodium sulfide battery, here also initially at low power values around 10 watt per kg, you are getting energy storage densities of around 140 watt hour per kg, whereas at high values of around say 4 or 5 into 10 to the power 2 watt per kg power generation, you are getting energy storage values of around 110 watt hour per kg. Okay. Some batteries have better performance indices, even though, so for example, in lead oxide batteries, even though the absolute values of mass specific energy density is much lower, it can generate high powers without degrading its energy storage ability significantly. Okay. Similarly, nickel cadmium also has a vertical, so ideally we should have a vertical plot and the plot should be as to the right as possible. Okay. So we see both nickel cadmium and lead oxide have nearly vertical curves, but the disadvantage is their mass specific energy storage density is already quite low. So that kind of ends our battery performance characteristics. We discussed how the current voltage curve, how the power curve looks like, how the energy storage and the power delivery there is a trade-off between them in batteries, how to evaluate the round trip efficiency, what is the importance of the electromotive force and what is the importance of the internal resistance. In the next class, we will begin to look at different types of batteries and discuss each type in specific details. So thank you for listening and see you again in the next class. Thank you.